It's time to get technical. In this episode, we're going to dig in and actually build some logic circuits. Simply put, logic is the electronic implementation of math. That's it. If you can write a mathematical equation in Boolean, you can then build that same function with electronic components. But to get started, I'm afraid we're going to have to start with just a little bit of math. We as humans count in a system known as decimal or base 10. The reason is pretty obvious. We have 10 fingers. If we were a species of intelligent octopi, we would probably be counting in base 8 or octal instead. But as humans, when we count, we go 0, because that is a real number. 1, 2, 3, 4, 5, 6, 7, 8, 9. There they are. The first 10 digits in the decimal system, and the unique name that we give to each one of them. But we've run out of unique characters, so we do something called carry. The Romans never figured this out. That's why a number like 1954 in decimal looks like MCMLIV in Roman numerals. The bigger the number, the longer the expression got until it was just totally out of hand. But with carry, you just tally and you go up. After the number 9, we carry the 1 into the tens column and then start over with the ones column. So we get 1, 0, which we call 10, 1, 1, 1, 2, 1, 3, 1, 4, all the way up to 1, 9, 19. But we've run out of unique digit combinations again. So we carry again and we keep on counting. And now the numbers are kind of starting to make more sense. We have 2, 0, which we call 20, 2, 1, 21, 22, 23, and so on. When we get to 96, 97, 98, 99, we don't worry at all. We just carry to a new column that we call the hundreds, and we keep on counting. 1, 0, 0, or 100. 101, 102, 103. But what does this have to do with logic? Well, as humans, we're very comfortable counting in base 10 because we always have our fingers if we get stuck. Computers and electronic circuits aren't so lucky. Sure, there have been attempts to make computers that could count in decimal, but they all had a similar problem, something called noise. If a certain voltage represents the number 3 and a slightly higher voltage represents the number 4, what happens if there's a noise spike at the wrong time? Was the resulting voltage trying to represent 4 or 3 or something else? Unless the difference between each of the 10 digits was big enough, noise was always lurking around causing problems. And if you made the voltage difference big enough, then 10 of them stacked on top of each other could result in some potentially dangerous voltages. So digital computers today reduce all of their numbers to just 2 voltages, on or off, 5 volts or 0 volts, high or low, 1 or 0. And since there are only 2 states, we call this base 2 or binary. Now binary follows exactly the same rules for counting as decimal did. We start with nothing, which we call 0. And then a single item we call 1. Hey, this is easy. It's just like decimal so far. But alas, we have run out of unique digits because we only have 2 to work with in the first place. So to carry is to the rescue again. Carry 1 to the column on the left and start over again with 0. I know, it looks suspiciously like 10 in decimal, but it's not. It's binary 1, 0, and it represents 2 items in decimal. Then we count 1, 1, which again is not 11. It's the number which represents 3 things in decimal. Following me? Now, we've run out of unique digits again, so it's time to carry one more time. 1, 0, 0, not 100, 101, and so on. Congratulations, you are now speaking in binary. Now that you understand binary and how to represent numbers in binary, let's take a look at some logic gates. Introducing the OR gate. It does just what the name says. If either A or B, or both of them, is a binary 1, then the output is a binary 1. If this isn't true, then the output is 0. And we could show this in something that we call the truth table. And here's its friend, the AND gate. If both A and B are binary 1, then the output is a binary 1. Otherwise, the output is 0. And here's its truth table. And finally, there's the buffer, which really doesn't appear to do much. Whatever you put in, you get right back out again. Input a 0, and you get a 0. Input a 1, and you get a 1. It's kind of the yes man of the digital world. So, great math, great diagrams, but where's the electronics? How do you make a circuit out of these diagrams and drawings? Actually, you've probably already done it in elementary school. It's just that you likely didn't call it by these logical names. Now this is the most basic of all electric circuits. It is a battery, a switch, and a light bulb. Close the switch and the lamp lights up. Open the switch and the lamp is off. Or think of it this way. Insert a binary 1 on the switch and you get a 1 indicator on the lamp. Insert a 0 on the switch and you get a 0 indicator on the lamp. Ladies and gentlemen, I introduce to you the logical buffer gate in all its simple logical glory. See, you've already built logic and you didn't even know it. Now here's the second one. You probably called it the parallel circuit, but see what it actually implements. If A or B switches, or both, are closed, the light bulb is lit. Only if both switches are open is the light bulb off. It is a logical OR. And the series circuit, which is really just implementing the logical AND function. Only if A and B switches are closed will the lamp light, otherwise the lamp is off. Now here's one you may not have built in elementary school because the exotic metal invertium is used in this switch and it's not very easy to come by, but it implements a logical inverter. Apply a binary 1 by closing the switch and the lamp is off, so the output is an inverted 0. Apply a binary 0 by opening the switch and the lamp is on, so the output is an inverted 1. There are a few more logic functions as well, but they are actually just made up of the basic logic gates you've already seen. We won't dig into detail at this time, but here they are. NOR, which is just an OR with the output connected to an inverter. NAND, which is an AND with an inverter. And finally, the XOR, or exclusive OR. I don't have enough switches and lamps to make one, but it would look something like this. You make one by ORing A and the inverted of B and the inverter of A. Its function means that one or the other, but not both, must be binary 1 for the output to be 1. And then its complement, the XNOR, which is all that, and then you just invert it. I know it sounds complex, but these simple circuits can be very useful. Okay, so we have logical functions, and we can build them with real electronics. How does that make a computer, though, that can add, subtract, multiply, and divide? I'm glad you asked that. Because just like in decimal math, we can add in binary. 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 1 equals 0 with a carry. But look at the truth table. Why, the first digit is just an exclusive OR. And the carry is the AND function. So you can actually add two binary numbers together, complete with carry, with just two gates, like this one. And with just a bit more work, you can make an adder that's as wide as you need. 8 bits, 16 bits, 32 bits. You want to do a subtraction? You just invert one number and then add them together. Voila. Well, how about multiplying? Arrange those same AND and OR gates together, and you can build a multiplier. So, what have we learned this lesson? We've gone from the basics of binary math to the symbols used in logic to some actual logic circuits that you can build. You are on your way to being a real logic head. Aha! So you're one of those people who sticks around until after the credits, eh? Now, perhaps you were wondering where you can get some of that mysterious invertium metal that we use to make that cool inverter circuit. The answer, of course, is it doesn't exist. Here's how the circuit is really created, which you can see if you lift up the knife switch and look underneath it. Hidden underneath this switch is a small circuit with a relay that uses the normally closed contacts to invert the signal. So when the top, the visible switch, is closed, the relay coil opens its switch contact and it's the relay that's actually powering the light bulb. So it's just a trick. There's no magic materials, but you knew that already, didn't you?